Well, good afternoon from IIT Kharagpur on this live session of soft nanotechnology. This is a new edition from this year's program where the candidates or the people who are attending this course or registered can get a chance to interact with the instructor directly. So the idea is that if you have any specific question, you can ask me directly using your chat box. You can key it in and I will try to take that question. I have received only a few questions which I will address straight away, but if there are no questions, I am sure many of you are watching me online. So I will sort of discuss about the course and what we have done and certain critical aspects about this particular course. Also maybe I will try to give you some sort of a clue about how you should prepare for the final examination, because I want as many of you who have registered, taken the trouble of registering, attending the lectures, attending the courses, please do participate in the examination. That's going to really help you. It really doesn't matter how much you score or you are worried whether you will do well or not, but it is very important to sort of sit for the examination and get yourself evaluated at what level you stand. I am sure if you are regularly attending these lectures, you must have learned something that is significant. Now the first question I have is from Pritam Das. The question is not exactly related to the course. The question says why nanotechnology is related to growth of economy. Honestly speaking, I will probably not prefer to answer this question. Nanotechnology is related to development of science, and any economy, if it wants to really grow and become a superpower, it needs to have a strong fundamental basis of research and development, and that is why nanotechnology can contribute. And therefore, you can actually try to do a bit of good quality science which will benefit everyone. It may not have immediate societal impact straight away, but if your work is really good, maybe somebody soon enough will pick it up, and maybe some industry will also pick it up and lead to some product development. I am sure in this course we have given clue for several such ideas. One of them, for example, is the so-called concept of the self-cleaning surfaces, which is based on the concept of hydrophobicity, a surface which is maybe structured or which has a low surface energy coating, and the contact angle hysteresis is much less, and therefore you can expect self-cleaning surfaces. As you see these days in large cities or many buildings, they come with shining glass facades, and during the lectures I have mentioned that have you ever thought how these facades remain so bright and shining, and the answer to that is self-cleaning coatings, and not too many of them are made in our country, and therefore you can sort of easily develop a technology related to this particular topic or area. Coming to the next question, which is from Mr. Shripad. How to apply this process for fabrication of artificial porous bone structure at micro level? Well, honestly speaking, development of artificial bone is a completely different paradigm altogether. You typically need ceramic materials like hydroepitaxide or something like that. I'm not an expert on that particular field. But what you can also do, I mean, once you transplant an artificial bone or any artificial organ, there are issues related to acceptance of the new organ inside your body, and there in fact some of the concepts that we have discussed here becomes very critical. I mean, for example, if you have tiny structures on the surface, the effective surface area of interaction might be higher, and that might lead to maybe some positive effects. But honestly speaking, this course is not exactly aimed at addressing the issue of how these processes are related to directly making some porous bones. Mr. Prashant Bhatnagar, welcome to this course. You have some question regarding the examination pattern, right? Yeah, of course you are supposed to go through the derivation, but yeah, I mean the question will be in such a way that you either pick up the correct answer or you just plug in some numerical answers just as you have done for your assignments, and therefore there will be no derivations straight away. But well, of course one can critically ask certain questions like boundary conditions in a particular derivation, or what are the nature of scaling. So you need to know at least the derivation and the outcome of the derivation, how it can go. You have another query regarding some marks in your assignment, which my TAs are taking care of, and we will get back to you. It seems there is something you have just written a numerical answer, but let us not get into that. You can always mail to us and we will respond. Now, we got some new question. So, how to get a protocol, practical knowledge on nanotechnology? Well, I think more than practical knowledge, this course is aimed at making you understand what are the critical aspects or scientific aspects of nanotechnology. Practical knowledge, if you want to get, I am sure you can sort of look into the Wikipedia, which is a great place to learn about these practical aspects, etc., etc., and therefore that is perfectly fine. But I guess there are several critical issues that is very special about nanotechnology as a whole, which I have already discussed in this course, and I have categorically mentioned about the first critical aspect of nanoscience, and that is the so called finite size effect. That is, you make things so small that your intensive properties becomes extensive. That is exactly what leads to these different colors or different size of nanoparticles exhibiting different colors, which are sort of commercially exploited now with LED lights that go on changing colors, for example. But this particular course, since we are bothered more about the surface patterns and things like that, I have categorically highlighted that the nanoscale is also a length scale which is predominantly dominated by van der Waals forces. And if you look at our lectures on the spontaneous instability and deweighting, for example, there you see a clear signature of how nanoscale or how the van der Waals forces acting at the nano or mesoscale, let us say about 100 nanometers, can be so destructive in completely destroying a film. So, these type of understanding is very, very important, because there can be many applications related to coatings. For example, many of us wear spectacles, and most of our glasses these days come with some coating or the other, right, which can be sort of anti-reflection, scratch proof, etc., etc. So, the issue is that if you would like to make your coating thick, it will sort of absorb some amount of incident light, which you do not want. On the other hand, you now understand that you cannot make your coating very, very thin, because then the coating becomes prone to these type of spontaneous ruptures. So, therefore, what you say as practical aspects, some of the detailed scientific issues that we have discussed as a part of this course can eventually be extremely useful. Similarly, addressing to another candidate's query regarding this, how these technologies can be taken forward, I just mentioned about the self-cleaning glasses, which are of course very, very practical. You see these type of shining glasses everywhere now in metros, big cities, tall buildings, malls, everywhere. So, there are very, very many aspects which are very practical, but they are related to some very fundamental and basics of nanoscience, which I have tried to highlight as a part of this course. So, Mr. Amar Ratan, transition metal dichalcogenides like MOS2 polymer for explosive sensing, is it a good research topic? Well, this has nothing to do with this particular course other than the fact that this is related to nano. MOS2 is one of the very strong and recent candidates for 2D materials, as you know, and therefore it is indeed a very, very good research topic, and 2D materials are great candidates as sensors. So, all the best for your research. Okay. So, it seems there are no more questions in the chat box, but that is perfectly fine. Feel free to come up with your own question as per your convenience. Now, in the meantime, what I will do, I will just try to sort of present a recapitulation of the course content that we have discussed as a part of this particular course. So, if you look back into how the story unfolded, we sort of had a pretty reasonable, pretty longish introduction on various aspects of nanotechnology, and of course with specific emphasis on surfaces. Now when we talk about surfaces or the nanoscale aspects, we essentially talked about two primary aspects. One is about thin films or ultra thin films, and the second thing was about the apparently easier nano patterns. So part of the course we dedicated towards understanding how to make such patterns, and there was a question about the practical utility. Now you after attending the lectures, I am sure you should appreciate that your all IC devices, the IC chips, microelectronic devices, they are fabricated based on some nano pattern. Their fabrication is associated or involves a major nano patterning platform, which is photolithography. And also if you wonder, as I have mentioned in the lectures also, that how with every passing year your devices are becoming smaller but the processors are becoming faster, it is entirely attributed to the fact that you are able to create narrower stripes based on photolithography. So that is something that is of course very practical, and I am sure that photolithography is a topic in which, I mean, it's offering a course is not an important parameter, but it is extensively utilized in the industry, but it is not covered in sort of a subject like mechanical engineering or chemical engineering, something like that. So I just tried to give a glimpse of how this method works. There are several aspects to this whole research area. For example, photoresist development itself can be a huge research area, exposure, development, the doping reactions, everything is a very detailed research topic. We did not go into any of the details, but the way I wanted to teach you, and that is also how I sort of prefer to teach in a class in Kharagpur, is that you have some idea, and if you need to go into the depth of these topics, you can always pick it up from the relevant literature. So in the meantime, we have another question for Mr. Gaurav. Nanotechnology works everywhere, is it so? Well, this can be answered more in a philosophical way. Partly yes. I would say that many of the apparent macroscopic phenomena, for example, or macroscopic cases where what you see, there are issues where the nanoscale phenomena or nanoscale morphologies sort of govern a major role. We have talked about some of these examples, for example, in our course. For example, if you hold the compact disc CD, look at the back side of it, you see the rainbow colors, right? Now this phenomena, CD is not a nanoscale object, it is a pretty large object, but that you see the rainbow colors is because of optical diffraction, the back of it, and which is related to or which is attributed to presence of some structures over there. Similarly, if you see a soap bubble, of course a soap bubble also you can see some bit of structural color, but even the formation of a soap bubble, you need to have the presence of the surfactant molecules, and therefore you now know that there can be issues related to micelle formation and stuff like that. So in a very simple way, I mean, you can think of why you always need a soap bubble, why you talk about a soap bubble, not a bubble out of plain water. It is because the presence of the surfactant molecules, the repulsion between the head groups sort of prevent the water layer from draining, otherwise you can't have it, right? So that way there are many application areas which involves day-to-day life, our existence, which involve some of the concepts that we have covered in this particular course. If somebody is using a contact lens, for example, it has to be kept wet at night once it's taken off from the eyes, and essentially the idea is that once you put it back, there should be a thin lubricating layer between your cornea and the lens, and whether this layer will remain intact or not depends on some lipid formation in your eyes, but for people this liquid layer somehow breaks down, they can't use a contact lens. And what is the phenomena that's happening? It's actually dewetting, nothing else. Similarly, when somebody is painting your walls and you always insist that please put 2 coats of layer, right? Why do you do that? You actually do that because you would like to have your coating or paint layer adequately thick, right? So that it is far away from this van der Waals force driven spontaneous instability, which are nothing but manifestation of some nanoscale interactions, right. So that way you see the effect of these nanoscale phenomena or the force fields in many of the macroscopic observation also. In other words, that you do not have to always observe these phenomena under a microscope. Chemical engineering second year project, I think it's Gowda again, and you want to start a chemical engineering second year project. You want to start a project on preparing a self cleaning surface. That's a very easy topic, very easily executable, but if you can come up with it, I am sure it will be very good for you. You can get good quality papers, or even if the product is really novel, go for a patent. One small advice I will give to the students or whoever is attending this session is that if you are planning to do some research, for example, in future, always be particular about one critical aspect, and that is what is novel in your work. I have seen many students who are about to start their research or project. You download relevant papers, read lot of literature, and then find out what people have done. Well, that is indeed extremely necessary, that to know what is the prevailing state of art. Don't always depend on or don't try to emulate what others have already done, because there is one limitation, that's not novel. So please try to search for something that is novel, use your brain, use your wisdom, use your intellect to come up with novel solutions. And always claiming that something is cheap and therefore it is novel is not a very good idea, because all these things, whether it is cheap or costly, easily executable or not, these are bit qualitative terms. But if you have indeed scientific novelty, then there is no doubt about the quality of your work. So please try to find out or do some science which is at the cutting edge, and you really don't have to worry whether you are doing from any college or IIT in India or somebody is doing it from US, because you can still compete with the best in the world if you conceive your problem properly and try to find out a proper answer and reason to solve the problem. I am sure there are many problems in our country which, with appropriate application of nanosciences and technologies, you can come up with excellent solutions. Well, Mr. Amar, you have a question why various compounds like silicon are indirect bandgap in the bulk but becomes direct bandgap semiconductor at the nanoscale. This is again something that you are asking, not exactly related to soft nano, because soft nano avoids silicon, right? The whole paradigm of this polymer related or soft surface related material is not to talk about silicon, and neither I am a silicon expert. But I guess if your question is appropriate, then it has again got to do something with the change in the band structure as a size of confinement or the finite size. But this is not a question that is related to this course directly, and therefore I really do not have the capability to elaborate it much further. Mr. Kunal Patel, Nano Titania for self cleaning, is it good to apply every area of the city? Well, your question itself actually brings so many questions into my mind. Firstly, how are you going to produce so much amount of Nano Titania? Of course, Nano Titania is well known for its self cleaning property, and if I am not wrong, it also sort of shows some photocatalytic activities as well. If you want to apply it everywhere in your city, you need large amount of these titania to be produced, and for that you actually need to scale up your whole synthesis process, because mostly people make it in some small amount in the lab scale, characterize it well, and that's all about it. So you really need to think about scaling it up, and then also come up or think about how to apply it in the form of a easily executable durable coating. And this coating, you really cannot rely on a technique like spin coating or dip coating, because you want to sort of put these coatings on pre-existing structures, for example. So you would eventually have to think about coming up with a solution like which can be simply put like a paint with a brush or a solution or something like that. Indeed, it's a very well thought out concept, but it involves significant issues which many industries will be interested in, to scale up the production of nanomaterials. So I think we are waiting for some more questions. It's good the type of response you are giving, so feel free to ask any question you want. I'll try my best to answer to whatever is possible. So I have a question from Mr. Shubhrojit Mohanty. Use of nanotech in computer science, use of nanotech in physical devices, vehicles, home appliances. Well, let's not limit our discussion only to nanotech. We have talked that in computer science, the faster processors, large scale memory devices, they are all fabricated because of extensive development in the area of patterning that we have discussed pretty extensively. I think there are some lectures, lecture 18 or something like that, where we have 6 lectures on photolithography. So kindly go through those if you have any doubt about them. Physical devices, well, of course there are a lot of work that goes in nanoscale devices like a single nanowire devices and stuff like that, where the entire physics changes. I am not an expert on that particular field, but you can look into some of the literature. Vehicle, well, there are a lot of areas. For example, you can come up with many types of coatings for the paints. You would like to have a paint that is far more durable. You may also want to come up with a formulation which may allow your paint or surface to become self-cleaning, so that particularly in a dusty country like India, you do not have to really worry about dusting your car very frequently. You can also think of an undercoat, for example, which comes in contact with mud and water and everything, and you can come up with a hydrophobic or a non-stick paint, for example, which will be very, very helpful. But you can also come up with anti-reflection coatings, for example, for the windscreen or the front glass of your car. See, I mean, if you can come up with a durable hydrophobic anti-reflection coating, that would be really wonderful, because you see many times if you are driving your car at night and then there is glaring light from the other side, it really disturbs the driver. So if you can come up with a coating that sort of reduces the glare, and simultaneously it is also hydrophobic, so on a rainy day, for example, where again visibility is compromised despite having the wipers, right. So you can combine all these things. These are doable things, people are working on these areas, so you can find application in vehicle. Coming back to home appliances, your non-stick, just visit your mom's kitchen or your kitchen, and the non-stick cookware, for example, is an example of a low surface energy coating, right. Because you do not want your your food material, particularly the oils, and probably as a part of this course you have now developed an idea or understanding that oils are low surface energy materials, because most of the oils are van der Waals liquids. So you do not want really the oils to spread. So non-stick cookware is already there, but more importantly, most of us use smartphones these days or touchpad devices, and one thing bothers us repeatedly, that the screens becomes dirty with our own fingerprint. So research is actually going on to come up with coatings, for example, or it's primarily coating, which can be anti-fingerprint. So these can be like oleophobic surfaces, which does not want or does not allow even oil to spread, right. So these are already coming up. These are all very advanced research areas, and you can imagine that most of the ATMs are now touchpad based, all our smartphones are touchpad based, and many times you will take your smartphone and rub it here, right, just to clean it. So if you can really come up with anti-fingerprint surfaces, which are essentially oleophobic surfaces, they will be really good, right. So there are a lot of applications of so-called nanotechnology in day-to-day appliances or day-to-day applications, right. So as my students prepare the next set of questions, let me just reiterate a little bit on what we discussed in the courses. And after we had a detailed introduction, and where we talked about certain phenomena that we all observe, like structural color, self-cleaning surfaces, we tried to go into the details of some basic concepts of surface and interfacial tension, for example. And for that we actually looked into two particular aspects. One is I gave you an idea about what are the different components of surface tension, now that you understand what is surface tension. And it turns out that the different components of surface tension are the van der Waals interaction and the acid base or the polar interactions, right. Of course, there can be, for a polymeric material, there can be other type of interaction, and the predominant interaction that is present in a polymeric material is the so-called steric interaction, which originates due to the entanglement effects, right. So, one can understand, so you can first search the net with the word entanglement, what it means, or I will give you a very simple example that will sort of give you an idea about the effect of this entanglement, and that is, suppose you would like to have some rice versus some noodles with a spoon. Repeat, it is a spoon. So, what is the difference you will observe? The key difference you will observe that if you have picked up 33 grains of rice on your spoon, all the 33 grains will sort of get transferred to your mouth. But in contrast, if you have picked up 18 threads of noodles, you might see that a few of them might slip out. And why it is slipping out? Because some of these long threads are entangled in the bulk of the remaining noodles. So, this is sort of, in a very simple nutshell, the effect of entanglement. So, in our formulation, though we have dealt a lot about polymeric films and surfaces, we have not talked about any mathematical consequence of this entanglement that is present in the system. So, of course, one can look into all these effects when talking about the effects of surface tension in more detail. For example, for polymeric material, surface tension, how it changes as a function of molecular weight, how it changes as a function of the architecture of the polymer chains. These are all very interesting topics of research where lot of activity, current activity is aimed at. In the meantime, we have some more question. Mr. Gauri Shankar, solar printers are available in abroad countries. Similarly, is it possible to develop large scale production of titania based solar cells? Well, I guess yes, but you have to understand that all the installations of solar cells that you see nowadays in India, and India is installing solar cells in a very large way, right? They are predominantly silicon based solar cell, because these are the ones that are sort of industry standard now, offering some 16 to 18% efficiency. Since they are bulk produced, unfortunately not too many of the solar panels are fabricated in India. They are very cheap and they are durable. In comparison, these titania based solar cells or the hybrid solar cells or the polymeric solar cells, they are far more at a research level as of now. Their efficiencies are far lower as compared to the direct bandgap silicon solar cells, and therefore it might actually take some time because they are before they are commercialized. But one thing is for sure, polymeric solar cells or hybrid solar cells, you need a lot of development and research in materials, which people are doing, and once the materials are standardized, the fabrication processes are standardized, then it is obvious that one can further bring down the fabrication costs and can come up with lower cost solutions. But as of now, taking your question again, yes, it is indeed possible, but maybe in the next 5 to 10 years you will see more and more installations with silicon solar cells. Right. So, Mr. Amar Ratan, you have a question. In solvent assisted exfoliation of layered compounds or layered materials, I would like to maybe modify your question a little bit. Surface tension of the solvent plays an important role during the time of ultrasonication. Explain. Well, it's a pretty easy question, and the concepts that we have developed is should be quite handy in explaining. See, when you would like to exfoliate something, you have these layers, right? And what you want, exfoliation is possible only when the solvent penetrates into the layers or between the two layers, only then it will exfoliate. So, eventually you would like to have a situation like this. So, solvent has got in and it has detached or flooded between the two layers, so therefore this layer can be exfoliated. Now, the question to ask is, under what condition the solvent will penetrate between the two layers. And if you now think, it is very simple, it is going to penetrate only when the layer of the or this particular material is wetted by the solvent, right? Only then it will penetrate. And how, what guarantees that whether a surface of this particular material, let us say A, is going to be wetted? It depends on nothing but the spreading coefficient, right? So if you have a solvent that fails to wet the surface of the layered material you would like to exfoliate, you can do any amount of sonication, but then you are relying only on the mechanical forces for the detachment, which is not exfoliation. So exfoliation is preferred only when the solvent sort of penetrates between the layers, and that is possible if the material under consideration is fully wetted by the solvent we are using. And then you can just write down the expression of spreading coefficient for complete wetting, and you will see. So we know it. So it is gamma S minus gamma SL plus gamma L. So all you need to know is the surface tension of the liquid and the interfacial tension between the liquid and the solid. Of course, you need to know the surface tension of the solid as well, and then you know that you are going to have a stable film, or you are going to have wetting if the summation of these two terms is more than this particular term. So that's how it stands. Mr. Krunal Patel, silver nanoparticle has antimicrobial activity. There are many such products in the market, but they are not popular, even if they are not hazardous. Why? Well, one thing I must tell Mr. Patel, your question is very generic, and please use the internet for this type of questions, because here I am sitting to specifically reply to questions that should come to you after going through the course. Why it is not popular? It might be related to the fabrication cost, availability, stability of these particles, because if you talk about very small particles, they might get agglomerated. But I am sure there are a lot of products which are using these type of nanoparticles, including some ointments for healing, faster healing, a lot of beauty products, for example, these white coating the cricketers and people who go out in the sun, they all contain nanoparticles. So I do not fully agree to your statement that these there are not dearth of products. It's not fully true. So Mr. Siddiqui, welcome. What significant role does simulations play in nanotechnology, if at all? Can you give a good application of simulation in line with the course? See, this course I have not talked about any simulation. We talked about some concepts related to the theory. So simulation is actually the next step. You develop the theory and then you write a computer code. But you can think, you can look into this whole concept of this stability, the theoretical concept of stability of ultra thin films, where simulation has played a very, very important role. You can look into the work done by Professor Ashutosh Sharma of IIT Kanpur and Professor Dipankar Bandopadhyay of IIT Guwahati. Both of them are simulation specialists. Ashutosh Sharma at Kanpur and Dipankar Bandopadhyay at Guwahati. Both of them are simulation specialists, and they have done a lot of simulation on stability of these type of thin films. The real advantage of doing simulation is, firstly, you reduce on the experimental efforts, because if you are trying to find out some critical concentration or critical parameter, etc., based purely on experiments, so you really have to do large number of experiments to reach at the optimum condition, which with a proper simulation, if you have understood the physics correctly, that's the most important thing, then you have translated it in the form of a computer code nicely, then probably the simulation, such simulations can guide the experimentalist to pinpoint what exactly needs to be done. But if it is not matching, then you probably need to look into the core of your simulation, including the boundary conditions and the governing equations and the simplifications you have taken, because high quality research is only possible when you have both simultaneous simultaneous execution of simulation and experiments, because ultimately if you want to create something, want to observe something, experiments are the only truth. Mr. Gowda again, when we supply electricity to a nanowire, then the electricity is continuous for many years. Well, I am sorry, I can't understand your question. Maybe it is true or not, I do not know. So, maybe if you can find out the answer, it would be good if you also let me know what is the correct answer. Right. So, thanks for all the questions that came in, sort of kept me quite busy. But the other intent that I have in this session is also to sort of have an overview about what are the things we have done. So, coming back to the basic concepts, we have talked about this hydrophobicity of a surface, and more importantly the so called Cassie and Wenzel states of wetting that we talked about, that is wetting of a surface on which is patterned, right, and you have seen that how it alters the wetting regime, for example. Examples of this are available in the nature. We have talked about some of the examples. The easiest example is the so called superhydrophobicity of a rose petal, of a lotus leaf, right. So, on a lotus leaf we all know that if a drop of water falls, it will simply roll away, and that is due to this Cassie state of wetting. But recently I have got very interested in another very fascinating type of hydrophobicity, and that is the hydrophobicity of a rose petal. If you look carefully, rose petal, if you put a drop of water on rose petal, it is hydrophobic. The contact angle is of the order of 140 to 145 degree. But if you even turn it upside down, the water drop does not move. It is totally different that way as compared to a lotus leaf. So, firstly, pedagogically it is not a superhydrophobic surface, because if you recall your course, contact angle hysteresis should be very, very less. Here it is totally different, contact angle hysteresis is significantly high in fact. So this is very fascinating, like you have a sticky hydrophobic surface, and therefore you might actually come up with some very novel applications in future. And this type of understanding, for example, emerges, or this type of observation you can correlate only when you understand the critical aspects related to different wetting states on a pattern surface, which we have discussed in the second module. The other important thing that we have also understood is about the Laplace pressure, that is a curved liquid surface which is at mechanical equilibrium may have a pressure jump at the boundary, which is not the case for a flat liquid surface, and we have talked about the Young Laplace equation. Then moving on to the third module, as I mentioned, we spent quite some time on the different nano patterning techniques. The first thing I told was the generic concepts. The generic concepts are three, like there can be a top down patterning approach or fabrication approach. This is not exactly patterning, this is any fabrication, or it can be a bottom up approach. And then since we talked about thin film instability and dewetting, we also know that there can be a self organization based approach. So the reason I say these are not limited only to patterning is, if you look at the way our houses or homes are built, they are actually built brick by brick. So that is actually a bottom up fabrication, bottom up making approach, bottom up technique. In contrast, if you ever care to worry about how the Kailash temple in Ellora was made, for example, what they did was, it was actually a small hillock, and where the stones were sort of cut in the desired shape. So you had something big and then you throw away some parts of it to make your desired shape or whatever. So that is exactly what is a top down fabrication technique, right. So then we correlated it to our lithography methods, and predominantly we talked about photolithography and various soft lithography techniques. So you may want to ask that I have mentioned somewhere in the course that photolithography, for example, is a top down patterning technique. Why it is top down? So it is because you have a photoresist layer, and then you all know by now the properties of photoresist, that is, if you expose it to light, depending on whether it is a negative photoresist or positive photoresist, it will either harden or it will degrade in property. So let us say you have a mask like this on top of which you have placed for creating the patterns, and then you have done your exposure. It is also acting as a good revision for all of you, and what you have is these areas have been exposed to light, right. So now you need to worry, so whether they have hardened or they have degraded, that depends on whether you have a negative photoresist or a positive photoresist, but whatever it is, these areas have changed their properties. Let us say these areas have weakened. So that means we actually have a positive photoresist. Now what you will do, during the development stage, these parts of the film will be washed away, they will dissolve. So you can see that you had something over here which is now gone. This area you have removed the material, and therefore this classifies into so called top down technique. Pretty similar is also the approach for some of the soft lithography methods, but honestly speaking, if you are very critical about soft lithography techniques, not all of them are top down techniques directly, but generically soft lithography methods or any patterning techniques are considered to be top down methods. For example, if you remember about micro transfer printing, which is the only method that is capable of creating 3D structures, it is actually a bottom up technique, because you sort of build layer by layer. One layer you first deposit on your substrate, then you add more layers. So it is all there. So I guess you are now competent enough to look at a process and find out whether it is a top down, it is a bottom up, or it is a combination of whatever. For example, this pattern directed dewetting, what we have talked about towards the end of the course, it essentially combines the concepts of both self organization as well as top down. Why? Because you typically start off with a pattern surface which is top down, and then you sort of create a film over that, and it evolves along the contours of the pre-existing pattern. So that is essentially a combination of self organization and top down approach. There can be many more examples of such. As I said, these are very open ended topics, so you can go on finding out how they can there can be combinations. So coming back to the course content, we talked about some of the soft lithography methods like nano imprint lithography, capillary force lithography, micro molding in capillaries, micro contact printing, etc. I would request you to carefully go through the slides and the lectures again, so that you understand what are the critical differences between different types of soft lithography methods. Right. So just now I received a question from Mr. Sri Pratap, how laser involved in nanotechnology. Actually that is a part of the thing we did not talk about. Laser and other beams like electron beam, ion beam, they are critical to direct writing methods like focused ion beam lithography, laser interference lithography, electron beam lithography and stuff like that, where what you do is you essentially raster. You have heard the word, or you are known to the word rastering now because of your lessons on AFM, where you would like your laser beam to pass according to a particular plan on a particular surface, and if the laser now damages the surface or removes some part of the material on the surface along the contours of its travel path, then you can create some structures. These are direct write methods. They typically work, they are a bit more complicated, and of course electron beam lithography one does with a PMMA resist, but focused ion beam is typically done with dislodging with an ion beam. You bombard a surface with high velocity ions with high energy, and you simply dislodge most of them, creating the structures. So yeah, indeed laser has a lot of application in this type of thing. Of course we have seen the utilization of laser in the so called beam bounce approach of imaging with an atomic force microscope. It is not exactly related to the nano, but you really need a highly coherent light to fall on the tip, and then it reflects back and goes to the quadrant photodiode, so that you can identify the variation in the topography. So coming back to the course content, we talked about the patterning techniques, and then as I was just mentioning, we talked about the very critical tool of nanotechnology, that is the atomic force microscope. Now my intention is not to really teach you about what are the techniques that are available for characterization of nanoscale features. A lot of people talk about that, and there are many techniques which are available for various types of applications, etc., etc. But I just wanted to highlight about one particular instrument, that is the atomic force microscope, because of two things. It is very unique. As I have mentioned in my lectures, that if you compare an atomic force microscope, or for example if you compare a scanning electron microscope with an optical microscope, basic principle wise they are quite same. So, right, so you are, in one case you are sending some optical light, in other case you are sending some wave of electrons, but you actually get an image of the surface, and most of the microscopes actually produces an image of the surface, and an image is actually taken on a 2D plane. So what you miss out is the information about the depth or the height, and it is here AFM stands totally apart because of its unique working principle. With an AFM you can always find out the true feature height, which we discussed, and I have mentioned in this particular class about how the AFM evolved from the concept of scanning tunneling microscope, which was the first invention like this, but it relied on tunneling current, and therefore it was only limited to scanning conducting surfaces. So based on that, the same inventors they eventually shifted to the atomic force microscope, which relies actually on the van der Waals force, which is omnipresent irrespective of the material nature of the surface, whether it is conducting, insulating, polymeric, metallic, whatever. And then I have given you a brief glimpse of the basic operating principle of an atomic force microscope, including the possible alignment and approach. Then we talked about the contact mode imaging, which is the most fundamental mode, and it was also the first one to come up. But then we realized that since we are talking mostly, we are interested mostly into the soft material, that is polymers and soft material like gels, contact mode can lead to significant damage of these samples, and therefore we talked about what is very popular these days is intermittent contact mode, which can be used very nicely for soft surfaces without any damage both to the sample as well as to the tip. That is what really makes intermittent contact mode very attractive. Then after we talked about the AFM, we eventually moved on to a very interesting topic, which is also very new because it is only for the last 20 years people have realized that these instabilities exist, of spontaneous instability and dewetting of ultra thin films. So here is a quick word of caution. If somebody asks you what is an ultra thin film, please do not commit any number. The way we have defined it, ultra thin film is a film where you have active van der Waals interaction or non-zero disjoining pressure between the two interfaces. Kindly go through the lecture notes to get an idea about these, and there we realize that that on a non-wettable surface particularly, one can correlate it to the sign of the Hamarkar constant or the magnitude of the disjoining pressure, right. On a non-wettable surface, if you have an ultra thin film, we also understood that you have fluctuations on the surface, which is attributed to the internal kinetic energy of the molecules, and these fluctuations typically are flattened out because of surface tension or the so called Laplace pressure. But in case you have it is on a non-wettable surface and the film is thin, we have done the derivation, so you can look into the expression for the effective interface potential, which the expression goes something like this, where you can also write it down as this, and you can find out the condition under which this oscillation will grow, right. And how it goes is, if you look at this part of the film, for example, here under one oscillation anyway delta H is negative. So what needs to be checked is, with reduction of film thickness whether the change in delta G, what is the sign in the change in delta G over there, right? That is the most important thing, because we all know that any natural process tends or proceeds in the direction of energy minimization. So over here, if as a function of, as a consequence of reduction of the local film thickness, if the delta G goes up, so your delta G, this particular term, delta G is positive, then of course this fluctuation will not grow, because by means of this fluctuation the film is, or the system is actually heading towards a higher energy system. That is something it does not want to do. But if it turns out that with over this area, this with this reduction in delta H or the film thickness, there is also this delta G, change in delta G is also negative, then what happens is, yes, the film might evolve, and that is the fundamental basis of this spontaneous instability. Now of course you can clearly see that if H is large, right, this term will tend to 0. So whether you have a wettable surface or non-wettable surface, it really does not matter, right. That is exactly the reason why the films, if you want to have a stable coating, would like to sort of have films which are adequately thick. That is why you do not have any such problem or catastrophe in terms of the coating application, because see, this physics is very rich. We spent 5 lectures on the physics of spontaneous instability and dewetting, but what needs to be understood that this type of dewetting or whatever is not at all desirable, right, from the standpoint of coating application. So there is now a lot of emphasis, lot of work is going on in stabilizing ultra thin coatings. So many of you ask questions related to many of you ask questions related to application of nanoparticles in commercial products, this, that, but reality is that these nanoparticles, if you add in some of these films which are very thin, right, it may so happen that they might suppress this type of instability. And what is the advantage? Then you can in fact come up with coatings which are very thin but which are stable, even on a non-wettable surface, and that is very attractive, because see, now with reduction of feature size, etc., in the electronic industry, you also have requirements for very thin resist layer for your photolithography, which we have also talked, right, because in photolithography you also deal with a very thin film of photoresist, and you do not want any of these instabilities to manifest in the photoresist layer, because then your whole photolithography process will be spoiled. But now you understand that you probably have to have certain minimum thickness of the photoresist layer in order to ensure that the resist layer remains stable. With these type of very advanced research, one can in principle make films which are very thin but which are also stable, and trust me, this has a huge application. So all the coatings that are placed on, for example, even simple stuff like your spectacles or glasses or sunglasses, they will become significantly lower in thickness, and you can also bring in nanoparticles with different functionality, so they can sort of, you can come up with a single coating containing these functional nanoparticles which will make it, let's say, and glare proof, scratch proof, and simultaneously smudge proof. Like if you continuously come in and out of a air conditioned room to a humid environment outside, sometimes you see a layer of condensation taking place on your glasses. So all that can be circumvented by a single layer. Similarly, on the front of these surfaces of different wettability or tailored wettability, there is a lot of advances that are taking place. For example, people are talking now about some very fancy surface called slippery surfaces, which are neither hydrophobic nor hydrophilic. These slippery surfaces are again inspired from the nature. Nature is sort of a warehouse for all sorts of exotic designs and functionalities. For example, so slippery surface is inspired by the concept of these insect eating plants or the pitcher plants. If you worry about, if you ever care to check out the literature or check out the functioning of a so-called insect eating plants, it has a pad, for example, which on which an insect may sit, and then the insect simply fails to fly out, and slowly the insect is drawn inward towards the insect to this flower or whatever it is. And similarly, one can come up with this type of slippery surfaces artificially, which are already being made. So these can be very useful in many applications, again some cleaning, etc., anti-dust surfaces. But another very fascinating area in which this research on hydrophobicity is moving, hydrophobicity or wettability controlled surfaces, is to look into surface of metals. Metals are crystalline materials, and therefore they have large surface energy because the molecules are arranged in a crystalline order. So in order to create a new surface, you need to spend a lot of energy, and if you need to spend a lot of energy, the surface energy is going to be high, and if the surface energy is high, material is typically hydrophilic, and therefore most metals are hydrophilic. But in fact, it turns out to have hydrophobic metal. So you cannot make really metal hydrophobic because that basically violates its fundamental properties, but you can definitely come up with coatings that can make metals hydrophobic, and then they can find a lot of applications. One immediate application is, for example, car bodies. They will, or the rusting will be significantly reduced anywhere. Also, if you specifically talk about a very chemical engineering application like condensation, you know probably there are two regimes of condensation, dropwise condensation and film type condensation. If you can have a condenser surface that is hydrophobic, right, you can probably enhance the regime of dropwise condensation significantly. So there were several questions on what are the applications of these work or nanotechnology in real life, in industrial products. So I think we have, in this 1 hour of discussion session, we have sort of talked about several of those. I think I have given you glimpses. Hopefully I have been able to motivate you why it is important or why it should be interesting to learn whatever has been covered under this particular course. So it's not exactly a pure science course where you only understand the fundamentals, but you have enormous amount of application in many things, and with appropriate mental investment, I would say, appropriate research, they can sort of lead to some significant products and technologies. So I think we are nearing the end of this very nice interactive session. So thanks to all the candidates who used our chat window to place your questions. I really appreciate it, and also felt good to answer to some of the questions. I would request all of you to go through the course content again. They are, I think, available at your login, and they are also available at YouTube. And if you have doubts, feel free to contact us through the designated mail ID, or you can write to me and forward it to my TAs, and they will try to help you. And I do hope that all of you will appear in the examination. You have registered for the examination on either of the dates, and wish you all the best. Thank you.